Hello, welcome you all to Friday. This is gonna be one of the weird Fridays that I actually lecture. I normally won't lecture on Fridays. I'll talk about what I mean by that next week as we approach a non-lecture Friday. But the plan today is to finish chapter 1. I might not make it the entire time today, all 50 minutes. It may end a little early. We'll see when I get well and where we're at. But yeah, I'm just going to continue on. I don't know. That was a whole lot of me saying basically nothing for a few seconds. So let's get into it. Well, I'd like to say where I left off, but I'm not going to do anything touching on where I left off. So I'm just going to move on. One of the things that we talked about last class, though, was the idea of units and how important they are. So what I want to start with today is conversions of units. That if I give you a value with set units, how to switch it to something else. Anytime your units are not consistent, you might need to convert. And anytime you're not in SI units, anytime you're not in mass in kilograms or length in meters or time in seconds, you're going to probably need to convert it from those units to those units. And so I just want to make sure we're on the same page for conversion of units. In general, units can be treated like any other algebraic term. If I let's say and if you start with the equality, like if I give you an equality, you can use that algebraically. For example, 1 inch equals 2.54 centimeters. I wouldn't expect you to know that. That just is a fact. And for the record, I will always give you conversion factors when they're needed. Now, if I told you something like 2x equals 3y, you can divide both sides by 2x. And you can do the same thing here. Units count as variables. So if I take this and divide both sides by 1 inch, if I divide both sides by 1 inches divided by 1 inches is 1. And I'm left with 2.54 centimeters divided by 1 inch is 1. And this will be a conversion factor. Anytime you want to convert units, what you're going to do is you're going to create a value of 1. A value of 1 to cancel out certain units to reach other units. And what you're going to do is if I give you a value and you want to convert it, you start with what that value is. Let's say something is 15 inches long. What is that in centimeters? Do that as an example problem. What you do is say, okay, something is 15 inches long. Let's convert that. And we'd start just by saying 15 inches long. And what I want to do is I want to not change the value. So I'm going to multiply it by 1. If I multiply by 1, the value doesn't change. But I'm going to multiply by a value of 1 to cancel out certain units. You see, if I multiply this by something with inches in the denominator and centimeters in the numerator, what's going to happen is algebraically, I'm going to have 15 times centimeters divided by inches. These inches can cancel out. But as I said, I have to multiply by 1. But look what I had before. We know 2.54 centimeters divided by 1 inch is 1. And so what I'm going to do is I'm going to multiply by a version with inches in the denominator because it was in the numerator, letting me cancel out my inches. And then I'll just multiply through. I'll just say 15 times 2.54 centimeters divided by 1.
Like, usually someone better is in this room. Why are you even here?
I don't know who that was. If that was that an actual question to me? I'm here because I'm teaching. So once I do this math, I get 38.1 centimeters. That means 15 inches is the equivalent of 38.1 centimeters. That's the conversion. Any questions there? Now, sometimes you might have units with multiple pieces. There might be the lab that opened up yesterday. Normally the labs, when they open it up, we already have covered everything. This was an exception this week, but by the end of today's lecture, you'll be good to do the lab. The lab's going to have you converting some mixtures of units, n divided by centimeters squared. Whenever you do it, you might need to use multiple steps, but just as long as your units cancel out, you can follow through the procedure. This next slide is just here in case you ever need it, just for your record. But I would always give these things as needed. Okay, I'm gonna do an example problem. And my example problem is about a real thing that happened. There was once a man named Oliver Smoot. And Oliver Smoot was at MIT and was pledging a fraternity. And this is back in the day enough that people didn't really enforce hazing. And they decided to measure the length of Harvard Bridge. Harvard Bridge being the bridge between Harvard campus and MIT campus. And how they measured it was in smoots. What they did is they made this guy lie down at the edge of the bridge, mark where his head was, and then get up and lie back down so his feet is where his head was. Then get up and lie back down so his feet is where his head was. And rinse and repeat and lay down over and over again until they figured out how long the bridge is. They found out that the bridge was 364.4 smoots long, which meant this guy on a cold October day, it was October in the thing, on a cold October day in Boston, laid down on the road 364 times, which sounds like it would suck. But anyways, Harvard Bridge is 364.4 smoots long. My question is, how long is that in meters, given that Oliver Smoot was 1.7 meters tall? So, I have my conversion. I know that one smoot is 1.7 meters. If I want to convert smoots to meters, I'll start with what I know. I know that the bridge is 364.4 smoots long. And I will multiply by a ratio. A ratio to cancel out what I want to get rid of and get what I want. I'm going to put my smoots on the bottom because my smoots was on the top. And I'll just throw in my numbers. My smoots can cancel and I can get a value. Fun fact, the same fraternity remokes the bridge every year. That picture there is a actual thing you can find on Harvard Bridge if you go there today. Also, Google recognizes Smoot as a unit, and Oliver Smoot once got the job as head of weight and measures for America. So it's actually an official American unit now because of this endeavor. Any questions with unit conversion?
Yes, I
Yes.
have one question.
Okay.
Since we know that a smoot is 1.7 meters, wouldn't it be easier to just multiply 364.4 by 1.7?
That's basically all I did in the end.
I mean, yeah, it still gets the same result and it's still the same
The
thing, but
reason why to do it like this explicitly is because sometimes you're going to be dividing instead of multiplying. And if you always write it out, you'll never mix up if you should be multiplying or dividing.
all right.
Also, it might come in handy if the units are raised to a power, which is what I'm about to do.
Oh, okay.
Okay. So let's say instead of straight up units, we have units raised to a power. Let's say you need to convert meters squared to meters squared to centimeters squared, or meters cubed to centimeters cubed. And just for example, let's say I have something that's 2 meters squared. What's that in centimeters squared? Well, we can go and figure out the conversion there. 1 meter is 100 centimeters, or 10 to the second centimeters. I don't know why I didn't write as 100. And so if you try to use the same logic and say, okay, let's start with what we know. We have 2 meters squared. I want to multiply by a ratio that cancels out meters and gets centimeters. There's 100 centimeters in a meter. Okay, let's multiply through. My meters cancel. Well, my meters don't cancel out. If I have centimeters squared and I multiply by this ratio, one of my meters cancel out, but they don't both. And then if I say there's 100 centimeters in a meter, that doesn't help me convert from meters squared to centimeters squared. That's the conversion from meters to centimeters, not meters squared to centimeters squared. And so for units raised to a power, I'm going to have to think about this differently. And actually, that's a lie. I don't have to think about this differently. I have to think about it the exact same way, to be completely honest. Just, I have to make sure I cancel everything out. And here's the idea. The reason this form of unit conversions works is because any number multiplied by 1 is the same number. But that includes 1. 1 times 1 is 1. And so if I want to convert 2 meters squared to centimeters squared, and 1 meter is 100 centimeters, I made my conversion factor that there's 100 centimeters per meter. That equals 1. But if I square that conversion factor, it's still 1. And so if your unit is raised to a power, you need to raise your conversion factor by that power. And what I'm going to do is I'm going to square that entire thing. I'm going to square my 100 squared. I'm going to square my centimeter. I'm going to square my 1. I'm going to square my m. And so instead of saying that there's 10 to the second centimeter in a meter, that could be there's 10 to the fourth centimeter squared in a meter squared. And get a new conversion factor.
That sounds like a
Was that a question? Or I heard noise, but any questions?
No, sorry, I was just unmuted.
All right, it's fine. It isn't really a problem. I just want to make sure I don't move on and not help people who need help. Not too worried. And so if I do the same logic, convert 2 meters squared to centimeters squared, I'll start with what I know, 2 meters squared. And I'll multiply by this new ratio to cancel out my meters squared. And I can say that when I cancel, it's 2 times 10 to the fourth centimeters squared. We good?
Yep.
Okay, let's do one that's a little more complicated. It's going to involve multiple steps and also something raised to a power. Next chapter, we're going to start talking about gravity. And I'm going to tell you the acceleration due to gravity is 9.81 meters per second squared. I don't know why I rounded to 9.8 here. We normally use 9.81. I think I was just trying to show something. And let's say, okay, this value, 9.8 meters per second squared. Let's convert it to miles per hour squared. Well, 1 mile is 1,609 meters. And 1 hour is 3,600 seconds. I just got that because there's 60 seconds in a minute, 60 minutes in an hour, 60 times 60, 3,600. This will go back to the why don't you just multiply it together idea someone asked earlier. This will kind of show it explicitly. So if I want to convert 9.8 meters per second squared, if I want to convert that in miles, my email just popped up. If I want to convert that in miles per second squared, miles per hour squared, I'm going to just have to go and do two things. I have to make my meters into miles. I have to make my second squared into hours squared. And what I'll do is I'll just do them one at a time and just do multiple steps on the same thing. This will also work. There's some on the homework where you're going to have to do multiple steps for the same number. There's one in fathoms, so you have to convert miles to feet, feet to fathoms. It'll be the same idea. And so if I wanted to do this conversion, I'm going to either start with the meters or the second squared. Doesn't matter which. I started with the meters because I felt like it. And I'll multiply by a ratio to cancel out the meters and get miles. And I'll say that 1 mile is 1,609 meters. Now, this is why you shouldn't just multiply together, because this shows me that when these cancel out, my number's on the bottom. So I'm not multiplying here, I'm dividing. And I'll multiply through. 9.8 times 1 mile divided by 1.609 times 10 to the third. And so 9.8 meters per second squared is the same as 0.00609 miles per second squared. You good so far?
Could you explain that again, actually, please?
So the general idea here is I want the units to cancel out. Since meters is on top, let me actually go back so it's not crossed out. Since meters is on top here, I'm going to multiply by a ratio with meters on bottom, so they cancel. And my ratio is going to be going from meters to miles, where 1 mile is 1.609 times 10 to the third meters. And so the 1.609 times 10 to the third, that goes on the bottom, so that they cancel out. The 1 mile goes on top, and I just multiply through. You multiply everything on top, you divide by everything on the bottom. 9.8 times 1 mile divided by 1.609 times 10 to the third second squared. Everything on top gets multiplied, everything on the bottom gets divided.
Why is there a 10 to the third? What is that? Doing?
Because that's the actual value. I wrote it in scientific notation.
Mhm.
If you wanted to do it in non-scientific notation, you could just say 1,609, but I wrote it in scientific notation.
Okay.
So 1 mile is 1.609 times 10 to the third meters.
Alright.
I'm
Thank
going to
you.
use scientific notation a lot in this class, which we covered. I want to say we covered last class and not Monday. Yeah, we covered that last class. Now, I didn't want miles per second squared. I want miles per hour squared. So what I'm going to do is I'm going to take that same number and multiply by a new ratio. And I want to cancel out seconds squared to get hours squared. Now, every time before, whatever we wanted to get rid of, we put on the bottom to cancel. But in this beginning bit, you can't see when I'm pointing. I don't know why I point. In this beginning bit, the second squared is in the denominator. And so if I want to cancel out second squared, I have to put it in the numerator to cancel out. Thing is, I don't know how many seconds squared in an hour squared. I know how many seconds are in an hour. So I'm going to write it like this and say that I want seconds on top to cancel. Well, 1 hour is 3,600 seconds. Now, at this point, I'm going to factor through this squared. Say seconds becomes seconds squared, hours becomes hours squared, 1 becomes 1, and 3,600 squared is 1.296 times 10 to the 7th. Just going to have to trust me on that math, though, because unless you want to use a calculator. This will allow my second squares to cancel, and I'll multiply through. 0.00609 times, this time it's multiplied because it's on top, 1.296 times 10 to the 7th. And there's my value in miles per hour squared. Questions? We good?
So I have a question with these units. Should the graph be something that we should recognize or be able to recognize?
What graph?
If I were to graph this because I've got a power of 1 on the top and a power of 2 on the bottom, should it look like a logarithmic graph or something?
Oh, but this has nothing to do with graphing at this point. The general idea here would be that for graphing, you have to have some sort of relationship between the pieces. And I'm not saying there's any relation. There's not really a relationship going here to be graphing. It's not an equation. The only bit that's an equation per se, really, is these. So you can't really graph this. It's not a series of points.
Okay, that makes sense. Thank you.
No problem. Any other questions?
Definitely is.
Well, right. Okay, if there's no other questions, I'm going to completely jump topics again, and I apologize for that. Once again, I'm just covering up, making sure we're on the same page for a lot of things you need to know. And this chapter is like that. So, I was just asked a question about graphing, so I guess I actually am tying into graphing now. One of the other things that's going to happen on this class, you're going to have to do a lot of unit conversions. We also have to a lot of deal with position, location, where things are. So I got to make sure you're all on the same page about coordinate systems. In physics, we define most everything using what is called the Cartesian coordinate system. And the Cartesian coordinate system, which I have displayed in the bottom on both bottom corners, is also known as the rectangular coordinate system, is a way to display the location of something, where you define everything as a point in X and Y. You start from a 0, which in my case is right there. I didn't actually put it in the actual corner just so that these fit. And you can say how far everything goes in X and how far up everything goes in Y. Points are labeled as X, Y, and you can say the location of each bit. When we're doing physics, we always want to work in a Cartesian coordinate system. Talk about how far something moves in X, how far something moves in Y. But here's the problem with that. Oh, sorry. And if it's three-dimensional, Z would be also there. You can kind of see Z sticking up here. Z. Oh. Z. But we don't have to do a Z if we're going three-dimensional. The problem is we need to work Cartesian coordinate system in physics. But as a society, we don't think that way. I have this monkey guy is kind of a slingshot. I got this thing I can launch, right? If I want to launch it up at an angle, I don't say I launch it so far in X, I launch it so far in Y. I launch it up at an angle. We don't work as societies on XY grids. Unless you're like in a city, like in New York City, you can kind of work in an XY grid because of blocks. But in society, it's normally you see something, it's that way. You go that direction, that far. You don't walk in perfect straight lines. And life itself works normally in a polar coordinate system. In a polar coordinate system, and I'm just going to go right over the picture I had there, all location is symbolized by the direct line to the endpoint and at what angle. That we're define everything as how far away at what angle. And think about it, it just makes more sense. If you're going to say how to get to something, you say, hey, go 20 feet that way. It's less likely to say, walk along this and make a 90-degree angle and go through. This is how we as humans work, how really everything natural works. The idea of going everything in perfect straight lines, this far in X, this far in Y, that's just a mathematical concept that has nothing to do with reality. And if I label where a thing is, you'll probably hear how far in what direction, not what you have in X and what you have in Y. And so we have a weird mixture here of what makes sense in nature and what makes sense mathematical that we have to use when doing math. And so we're going to have to make sure we can bridge this discrepancy. And so we have to be able to convert between a distance and an angle, all in theta, and X and Y. And the secret to that, how to do it, is trigonometry. Now, trigonometry is not required for this class. That's because all the trigonometry you need to know to pass this class, I will teach you. And most of it I'm going to do right now. Some of you have probably heard the phrase SOHCAHTOA before. If you haven't, SOHCAHTOA. SOHCAHTOA is a way to remember as a few phrases. And the phrase is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And what that really means is that any angle, if you have a triangle and it's a right triangle, so one of the angles is 90 degrees, and we're talking about coordinate systems. So we're always going to have a right triangle because X and Y are always perpendicular to each other. That if you have a right triangle, any of the angles, except for the one that's 90, we can say the sine of the angle is opposite over hypotenuse, is y divided by L. The cosine of the angle is adjacent over hypotenuse, is x over L. And the tangent of the angle is opposite over adjacent, is y over x. If you measure your angle from the horizontal, and okay, I'm going to get into this a lot more when we hit chapter 3, but I'm going to say this now. Always measure your angle from the horizontal. If you don't measure your angle from the horizontal, find out what the angle from the horizontal is and do it there. There's only one exception all class long we're going to have to do with that. It has to do with ramps. We'll see it in chapter 4. I'll talk about that then. But if you measure your angle from the horizontal, and you always should, we can use this triangle, or this triangle, because it's the same one in real life, to relate x, y, L, and theta. And we'll use this, that if you are given all and theta, how to get x and y. Because in this, if I measure my angle from the horizontal, if If I measure my angle from the horizontal, opposite over hypotenuse is y over all. That means the sine of this angle is y divided by all. The cosine of this angle is x over all. The tangent of this angle is y over x. And if I take these top two equations, and for both of them, I'm going to multiply both sides by all, and I get these right here. Anytime you're given a direction and an angle, if you need to break it to x and y components, though, as long as your angle is measured from the horizontal, which it should be, the y component will be all sine theta. The x component will be all cosine theta. And so by knowing the length of this green arrow and that angle right there, I can instantly know the length of x and the length of y, the length of the blue and the red arrows respectively. Well, that was backwards. The layer of the red and the blue respectively. Because all I'm doing is I'm taking them and splitting them into their components, their x and y components. Anytime you're given a vector that has direction and magnitude, split it to x and y. Okay, any questions though? Now, this works going that way. If I give you all in theta, you can get x and y. But let's say you take your all in theta, you get your x and y, then you do some science to it, and now you want to go and report back to, a common person. They don't give a shit about your x and y values. You might have to go the other way and go back. If you have your x and y, though, you can get your all in theta. To get all, we can use Pythagorean theorem. Now, you might be familiar with Pythagorean theorem as a squared plus b squared equals c squared, but in physics term, we normally say all squared equals x squared plus y squared. And this kind of shows it explicitly, this GIF, that it works. And so what you can say is your x component squared. So the length of this red arrow squared plus the length of this blue arrow squared is the length of this green arrow squared. That is what it says. And so if you ever know x and y, you can get all. That only gives you all, it doesn't give you theta. But the third part of SOHCAHTOA, the TOA part of SOHCAHTOA, was that the TOA part of SOHCAHTOA was the tangent of theta is y over x. And that means the angle, theta, is the inverse tangent of y over x. And so you can always find the angle just by taking y divided by x and taking the inverse tangent. Now, keep in mind, this will only work if your calculator is in degrees. I would recommend right now putting your calculator in degrees and keeping it there. Yeah, need to be in degrees. One other thing with this, let's say I'm doing the TOA part of SOHCAHTOA, and I say, let me just get rid of my axes, I don't need it at the moment. Let's say I have this set up for my y and x, and this setup for a different y and x, right? And let me just make up some values. I actually know the length of these because I made them. This is, let's say this guy is 3 meters, which does not the scale. This is 4 meters, 4 meters, 3 meters. I would say this is the positive direction. This is the negative direction. Oh, sorry. These are positive direction, positive direction. They're both positive. But down to the left, I would call both these the negative directions. We'll get into that more next chapter, what I mean though. If I was to divide 4 divided by 3, and also divide -4 and -3, I'd get the exact same numbers. When you do this equation, your calculator will always assume that x is a positive value. If at any time your x is negative, you must add 180 to the answer found. What I mean is to find angles. The equation really is theta equals inverse tangent of y over x if x is positive. Theta equals the inverse tangent of y over x, then plus 180 if x is negative. that if x is positive, just do the inverse tangent of y over x. If x is negative, after you're done, add 180. Any questions? Now, once again, make sure your calculator is in degrees. If you're in radians, you're going to get it all wrong. Eventually, we'll use radians in this class. I will let you know when that is. I will have a slide kind of like this one saying, oh shit, we need to be in radians now. We can worry about that then. But make sure you are in degrees. All right. This is actually the last topic for today. So where I would go now normally is an example problem to work through. But I'm about to do our first word problem. And so I want to do a quick pumping of the brakes, slow down for a second, and talk about solving problems before I go and do a problem with this. This isn't a math course. Math course, you're just doing pure math for the sake of doing math. Physics is using math to explain the real world, or in my case, my deluded fantasies and Pulp Fiction. Mechanics problems will always be word problems. That's all we're going to get. I'm going to give you a situation. You're going to need to figure out what the situation is asking for and solve it. How to solve a word problem. You should always follow through these steps. Step 1, draw it. I don't care how good your math skill is, draw something. You're going to learn over the course of this class how crappy my math skill is. I don't usually use Photoshop to defend me. Once you draw it, collect all the variables. Look at everything you know. What were you given a value for? And write down its symbols. Were you given a value for x? Okay, we know x. Were you given a value for y? Do we know y? And so on. Make sure everything is in SI units. Kilograms, meters per second. If it's not kilograms, meters per second, convert. And then I didn't say this, but collect all the variables. Also write down the one you're looking for. And at that point becomes the very hard part, which is figure out what the hell equation you're doing. Which equation to use is always going to be a matching game. What you do is once you collect your variables and the variable for whatever you're solving for, you just find which equation has all the same symbols. If I need to solve for x, I need an equation with x in it. And you play a matching game. Once you're done, you can make sure you answer the question. Make sure you have the correct units. And make sure it makes sense. I did my first semester ever teaching. I did a problem about a meter long metal ball that someone was pulling on, and they had to figure out how much longer it got. And multiple people in the class got 10 to the 20th meters, which is actually longer than the known galaxy. And they didn't think that something that was a meter long pulling with a normal force would get 10 to the 20th meters long. It's because they multiply by 10 to the 10th when they should have divided. Make sure the answers make sense. They won't always make physical sense when I do comic book problems, but if they really don't make sense, I normally comment on it. Now, these steps, there is a video you can watch on it. I am not going to play the video because I feel weird about using other people's YouTube videos on my YouTube. I will sometimes do it anyways. I actually have some videos that I'll ban in Turkey for copyright infringement, but only in Turkey. But if you want to watch on your own, you can. I also once gave a whole talk about doing this. So there's a PowerPoint on Vanco Hall in the supplementary system information section on how to solve word problems. That's all about Jon Snow. So you can watch those on your own if you want. Also, I do want to stress drawing a picture is important. Don't worry about details. I have seen many exams where people have spent a lot more time drawing the picture than they have solving the problem. Don't worry about that too much. But all of this was a segue. Well, not really a segue. All of this was an interruption. See, what we are talking about right here, or what we were talking about right here, is we were talking about trigonometry. So let's go back to that, and let's do a problem. And my problem is, Laura Croft from the Tomb Raider games slides down a zip line to get to the bottom of a 30-foot high ledge. You can see it in GIF form attached. If the zip line makes an angle of 15 degrees from the horizontal, how far does she move horizontally? And also, how long is the zip line? Also, what happens to that torch is another good question, but that's going to be unrelated. So, let's solve this problem using trigonometry and the steps I just covered. So I want to start with drawing it. So here's my drawing. My zip line is going down a length all at an angle theta. And I talked about how far she moved horizontally. That's going to be my x. And y, oh no, y is what I know. It's a 30-foot high ledge. I don't know all. So there's my drawing though. She's going down a zip line at some angle. My next step, what are my knowns and unknowns? So let's look what I know. I say she's getting to the bottom of a 30-foot high ledge. That means that's this. That's how high it is. So that's going to be my y value. That if just a 30-foot high ledge, y is 30 feet. And the zip line makes a 15-degree angle. So I know y and theta. For part A, how far does she move horizontally? That's x. So part A, I'm looking for x. Part B, how long is the zip line? For part B, I'm looking for all. I always recommend listing out your knowns and unknowns like this. It makes life easier. Any questions there so far? Yes, I constantly keep playing with a slinky. It's on my desk and I can't leave it alone. So, next step, check if they're SI units. That's in feet. Feet is not an SI unit. So screw that noise. We need to convert that. I'm going to make myself some more space by moving some things out of the way. And say, okay, I said y is 30 feet. I can't work in feet. Now, I happen to know that 1 meter is 3.28 feet. And if you don't happen to know that, I will always give these conversion factors. And so I'm going to convert my length. I'm going to multiply by a ratio to cancel out feet and get meters. So I'm going to multiply by a ratio with feet in the denominator and meters in the numerator, letting my feet cancel. Oops. And so I can do this math and say 30 times 1 divided by 3.28. That's 9.15. And so I'm not going to say my height is 30 feet. I'm going to say my height is 9.15 meters. And I'm going to erase the height I had before and put that. Oh, that shouldn't have done that like that. Oh, that didn't. What's going on here? Sorry, I'm having weird issues. Okay. Get back. Okay. This is where I was? Yep. Sorry, PowerPoint just crashed a little bit. Okay. So I'm going to say my height is 9.15 meters. And I'm going to put that up in the top. Now that I have that, I'll look at all of my equations. And I have 4 equations I covered here. Y is all sine theta. X is all cosine theta. All squared is x squared plus y squared. The tangent of theta is y over x. Those are the equations we covered a few slides ago. And say, okay, I want to solve for x. Well, if you look, if I'm solving for x, if I'm ignoring part B so far, because I'm not doing that yet, which is solving for all, I would say I know y, theta, and I want x. So equation 1 has an O in it. Don't know all. Equation's gone. Equation 2 has an O in it. Don't know all. Equation's gone. Equation 3 has an O in it. Don't know all. I have to use this last equation because that matches what I know. I know y, I know theta, I want x. And so I say, okay, there's my equation. The tangent of theta is y over x. So I will solve this. Now, I always recommend rearrange equations without plugging in numbers. The sooner you plug in numbers, the sooner you make a mistake. A 23 becomes a 32 very easily. So I'm not going to plug in any numbers. I'm going to say I want to solve this for x. Let's rearrange. If I'm going to rearrange this, I need x alone on the left. So I'm going to multiply both sides by x. I will then divide both sides by the tangent of theta. And I'll say x is y divided by the tangent of theta. And I'll just plug numbers into this. 9.15 meters divided by the tangent of 15. And I'll get my value for x. Any questions here?
Are these the type of questions that's going to be on the homework?
Yes. For chapter 1. Chapter 1 will all be unit conversions and then trig. Moving forward, they'll be much more difficult than this one. This is pretty straightforward, but for chapter 1 it will be. Now the other question is, how long is the zip line? That's going to be the value for all. So now we're saying, okay, let's solve for all. And so I'll look at my equations again and say, you know what? I want to solve for all. Equations 1, 2, and 3 all have all in them. I can use any of those equations. It doesn't matter which one. I chose to use the one with the square roots just because it's simple. And I'm just going to take the square root of both sides. If I take the square root of both sides, I'll say all is the square root of x squared plus y squared. Well, I'll plug in my numbers, square everything, add them together, and square root. And that's how long the zip line is. Questions? Okay. With this problem, I did 3 major things you're going to have to be prepared for. 4 major things you have to be prepared for this semester. And I'm kind of throwing you in the deep end with this problem a little bit, but at least I acknowledge it, I guess. Which is, you have to be prepared for word problems. It's going to be the entire class. Your homework will give you a lot of practice of this. The homework has a lot of old exam problems on it. Chapter 1 doesn't really have many old exam problems because I don't normally have an exam problem from chapter 1. You'll learn why when I get closer to the exam. But your homework in general have a lot. So you have to get used to word problems, figuring out how to solve them. We gotta have to deal with trigonometry. That was the point of this one. But there's also unit conversions. And also just the algebraic rearranging I was doing. So that is the end of this chapter. But I do want to, with my remaining 7 minutes, I'm going to use some of it, not all of it, make a comment about all that stuff. And mostly about your first lab. Your first homework is, I need to update. Your first homework is due Wednesday. And is going to be about unit conversions and trigonometry. You can already access it. You can start it. It's right there. Your first lab is also open. And this first lab is doing basically this stuff. The lab itself is all about how to make a graph, which I mentioned in class a little bit, but there's also videos on here on how to do, and also how to do unit conversions. Now, for the most part, the post-lab questions are about the lab, but lab 1 is not. The post-lab questions for lab 1 are all about the algebraic rearranging. It's going to be all about, can you rearrange certain equations? Because one of the things that we're going to do a lot in this class is we're going to rearrange things. I'm going to say things like, oh, this was me just hitting buttons, that if P equals F over A, solve for A in terms of P and F. The first labs problems are going to look like this because I want to make sure we're all on the same page for algebra. If you don't know how to do some of these, come to my office hours. Come get help. I'll help you. But we have to make sure we're all ready for what is to come, which is a shit ton of math rearranging and trig and unit conversions. So I have it there to help you. If you do have a hard time with the algebra, I do have an algebra review at the bottom, right above my solving word problem thing I spoke of. But that is the general idea. Other than that, that's chapter 1. If you need any help, please come get it. Homework is due Wednesday, lab is due Thursday, and that's going to be true basically moving forward. Any questions before I let you go? Well, I guess not really let you go. In a classroom, it's let you go. Online is you can really sign off whenever you want, and I have no control over it. Are we good? Okay. Have a good weekend. We'll see you next week. When next week we start actual physics. None of this prerequisite stuff. Bye.